All right, I'm gonna get out of the way and put our president up. Ready to go.
All right, can you all hear me, everybody? Thumbs up from the remote gang? Awesome. Okay. Welcome to the November 2022 meeting of the Warren Astronomical Society. I am your president, at least for another month. And I'd like to see if there's any new people joining us tonight here in the Cranbrook Auditorium. Okay, how'd you find us, sir? Internet, cool. What's your name? Jeff, welcome, Jeff. Yeah, we've got Jeff in NASA gear and Jeff in Pistons gear. Excellent. Okay, so a couple of things tonight. Ground rules for the meeting. We are dispensing with the short talk so that we can do the elections. We do need to be out of here on time, not just because Cranbrook is very nice and allowing us to come in, but because the red coat doesn't let you order anything until after 10:15. So if you get there after 10:15, you don't get to eat at the red coat anymore. Also, we have snacks. Mark Kedzier has worked out a plan to hopefully have safe-ish, well-contained, not free, observing the rules here at Cranbrook, snacks. So they will be $1 for a bottle of water and 2 snacks, Mark? Yes. And then 50 cents if you want more snacks. So we will have snack time during the break. We also have a special opportunity tonight if you want to see Sue, the exhibition that is currently here, temporary dinosaur exhibition at Cranbrook, starring Sue, the famous T-Rex skeleton. They have it open. You may partake of Sue during the break, or if you get bored of the officer reports. If you're running for office, please don't bail out of the elections and go see Sue, because we need you on the spot. So anyway, Sue tonight, so check it out. I know a couple of our members, Micah Dowd, Laura, have already had the chance to look at it. So, run through it. It's right behind us here in the basement. Okay, presidential report. Everything is going pretty smoothly. We are looking forward to assembling the banquet, which is going to be here in lieu of a normal Cranbrook meeting. So it's going to be a hybrid format with a virtual guest, but we are going to have real raffle prizes that Mark Kedzier is currently busy getting. So that should be a fun night with a very cool speaker that I saw in Vermont, and it turned out he was a friend of our treasurer Adrian through the Global Star Party, so it's all good. We are looking forward to bringing this to you. Also tonight we have a lunar eclipse early in the morning. So we don't have any outreach events because nobody wanted to do apparently recruit us to do an outreach event in the morning, Monday night. But if you have any desire to go out and see it, we have quite a few people who are planning their own little adventures. I know Adrian's going out to the Thumb to hopefully take pictures. Yeah, so if you want to catch the last total lunar eclipse of not just this year, but until 2025, it's tonight. And the weather looks pretty good, right? Yeah, weather looks promising. All right, over to Bob at the first VP desk.
Hi, everyone. Okay, yeah, our banquet, we're having, correct me if I'm wrong, Kareem Jafar is his name? Yeah, he's going to be speaking at our banquet, which is going to be pretty cool. He emailed me and he said that he'd like to talk again at some future point. And he gave a whole bunch of topics, and one of them was getting youth involvement in astronomy. And I would certainly like to see a lot more of that. I mean, the last time we've had youth here was John Blum's granddaughter. So, when I was 8 years old, I was an astronomy fanatic. And if I had known this club existed, I'd have been part of it. So yes, I'd like to see a little bit more youth engagement. So our talks for this year are filled up. Could use some talks next year. I'm looking at getting Heidi Hamill, who I did a podcast with Brother Guy, and it's a very cool podcast. She's a fantastic speaker. I'm looking at also getting Paul Gilster. He's a guy who wrote a book called Centauri Dreams, which he covers every single idea ever thought about interstellar travel and put it in a book. And I have a copy of it. So I'm going to try to get him to talk. But our membership, if you would like to give a talk, please, anything, if you're interested in any aspect of astronomy, start writing down some notes when you think about it and come up with a presentation and come on up here. We've had people give first-time presentations and be scared to death. And after the first or second one, you're not scared anymore. So come on, give a presentation up here. That'd be great.
All right, thank you, Bob. Riyadh turned in the report digitally in the WASP. I wanted to go over the highlights of the outreach report where they had poor seeing the night of the 22nd, but good enough time that they kept the party rolling until 3:30 in the morning. So good old-fashioned night of observing at Stargate, seeing Saturn, seeing deep sky objects, seeing double stars. Jeff McLeod brought his spaceship's Gemini capsule simulator, which I call the Gusmobile. And so Riyadh and Jeff and the crowd had a really good night. So next one is going to be the 24th of November. Fingers crossed that there's at least as decent skies as we just had. So all good there. And Bob is showing us sunspots. Okay. Who's next? Oh. Yeah, how about the treasure? Come on, Adrian. Give us a good word.
All right, I'm here with the Treasury report. The big number's in my hand, and there's a big number. We've been hovering around the $30,000 mark for quite some time. As we move out of an official pandemic, which we haven't yet, but socially, of course, we're all here. As we move out, more opportunities to invest money in different ventures for the WAS will probably come about. Please vet any ideas you have through the board. That includes any new refractors, Bill. If you want to upgrade your equipment, I don't know if we'll approve it, but we'll entertain all ideas. The rest of the Treasury report is in the WASP, and you can look at the numbers. We spread our numbers between PayPal, a main bank account, and I think those are the only two. Oh, and cash, which I have brought here. So if you for the snack drive, we will be able to make change if you only have big bills. And other than that, that's my report. Questions? treasurer@warrenastro.org. If you want to check your membership status, if you want to become a member, looking at you in the Pistons hat, if you are interested in joining, come talk to me. And that's it.
Thank you, Adrian. Next on deck, we have Kevin at the outreach desk.
Just a few things. Dale Parton's doing quite a few outreaches. He is doing a talk 27th for the Mid-American Atheist and Humanist Association. And then December 10th, a Christmas Star or talk. I can't remember the organization, Dale. Seven Ponds Astronomy. Mark Kedzier is doing a talk at the Warren Library on 9th November on telescope viewing. Bob Tremblay is doing one in February on the sun. Adrian and Jeff supported an outreach event at they're given that at the Belle Isle Dark Sky Park. It's so dark. Yes. It was Megan McAllen. Is that who you? Belle Isle. Sorry. Yep. Group.
We must have saw 15 to 20 stars.
Oh. But at least you could point them out because nobody knew which ones they were, so.
Yeah, 300 people from the city of Detroit come out and look at Jupiter, Saturn.
Yeah. Yeah, it's nice, right? I think it's great. And then Bob Tremblay's, you're gonna see an email. It's for supporting astronomy at the beach for 2023. There's a meeting, first meeting, the 10th November at 7. o'clock. So he'll send that out if you're interested in supporting it. Sorry? The 10th. And please do, okay?
Awesome. And while we were going through that list, I remembered that I had done a talk at the Ford Club last month, actually 2 months ago, because it was September, and I forgot to tell Kevin, so bad me. Okay. It was a reprise of my Apache Sitgreaves talk that I gave here. It was introducing our comrades over at the FAC to the glories of Steve Agus's place. Okie dokie, over to Dale at Publications.
Thank you, Diane. The WASP is online for November. I also want to point out that I appreciate all the articles and submissions that come in, and I'd like to encourage other members to go ahead and send in an article, anything to publisher at warrenastro.org, and or publications at warrenastro.org. Or you just send it to the WASP, I think, at Warren Astro. But it's been a pretty full year of articles, and now to keep the ball rolling. Thank you, Diane.
Thank you, Dale. Hopefully you'll get your movie reviewer back in January. And last but not least, we got Mark Hedzie, the secretary, with a special announcement. Calendars. Okay, in addition to the minutes being in the WASP, we have 18 calendars left, $20 a piece. You can, if you have a mobile device that is connected to the internet, you can pay online via PayPal right now. Otherwise, Adrian is here to take your money. And they are lovely. I just picked up my 3 calendars tonight. All right, that is the business portion of the meeting. On to subgroups. Bob was waving around. Okay, you're going to broadcast the sun for us because the sun's got something going on. All right. Solar Marty, do you have anything to add? Come on up, Marty.
Well, the sun had been mostly quiet for the past month or so, but just a couple days ago, we got a pretty good couple of large sunspots on the sun right now. Just rotated on within a couple of days, so definitely going to be around for another week and a half. So I recommend you get your scopes out, or even they're kind of big and close to each other. So try maybe some eclipse glasses and see if you can see them naked eye. Maybe be able to pull them out if you got better eyes than me. So definitely want to get those solar filters out now. And I wanted to say hi, Rick Gassett. It's been a while.
Yeah, it's nice to see some people have rejoined us after quite a bit away. All right, then. Double Star Group is going to meet at the next open house. They did get to see some double stars, as Riyadh reported in the minutes. And here comes Bob showing sunspots. Yeah, come on up. Let's do it. Here. Post the link. Do it. Yeah, let's do it.
But
I think it's kind of washed out, but
there we go. All right. Well,
I see spots.
there's a response to you, Marty. Rick has a message for you. Thank you, Rick. Okay, thank you, Bob. On to a discussion group. Discussion group Captain Jeff McLeod is still looking for people. If you are willing to host, let Jeff know. We may have be reconvened at Wayne State. That'd be cool. Okay. Remember, our November typical discussion group is not happening at John and Rosie's place because COVID is not over, and they've had quite enough of it. Thank you very much. So we absolutely respect that. And if we have to wait until warm weather to start having backyard parties again, hey, them's the breaks. Okay. History subgroup. I think we have some adventures of the Detroit Astronomical Society in this month's WASP, correct?
No.
Oh, I thought you had something in the archives.
No, I didn't, but I had mentioned before, in fact, if you read the article in the WASP, I had mentioned before that in 1999, I had every single printed issue except one, August. And I got to looking at it while I was perusing the directory for some other stuff. And it dawned on me that a lot of what actually shows up in the printed WASP was there online. And there's not a lot of difference between the other online WASP of that year and what was printed. Just a couple of minor things were missing or different. So I thought I'd try to recreate the WASP. And if you look at August of 1999 in the directory, you will see my version of that month's WASP. And hopefully you'll hold up against the real one whenever it shows up.
Fabulous.
Yeah.
Archaeology from the days of Web 1.0.
Oh,
All
yeah.
right. Okay. 7:47, we have a little bit of time for observing reports. Do we have any observing reports? I would hope we have quite a few. Okay, we've got first David and then Dale Hollenbaugh, and then we'll go to the audience here in Cranbrook. Take it away, David. Can't hear you.
think he muted. Yeah, he's not on mute, but the camera is on mute.
No, I think he's on the wrong mic.
You hear me now?
Oh, there he is.
Okay, great. Okay, we're
Shout.
certainly hoping to get a good eclipse tonight. And the sky is very clear here. And I'm looking forward, I'll be up the entire night to enjoy the eclipse. And for my poem tonight, I would like to quote Thomas Hardy's At a Lunar Eclipse, where he wrote this in over 100 years ago in 1903 after seeing a lunar eclipse over London in 1902. But this poem is so relevant for what's going on today, if you think about the war in Ukraine and everything. So here goes. Thy shadow, earth, from pole to central sea. I'm allergic to this poem. Once more with feeling. Thy shadow, earth, from pole to central sea, now steals along the moon's meek shine in even monochrome and curving line of imperturbable serenity. How shall I link such sun-cast symmetry with the torn, troubled form I know as thine? That profile, placid as a brow divine, with continents of moil and misery. And can immense mortality but throw so small a shade, and heaven's high human scheme be hemmed within the coast yon arc implies? Is such the stellar gauge of earthly show, nation at war with nation, brains that teem heroes, and women fairer than the skies? Thank you very much, and let's all get a good eclipse tonight.
Thank you. All right, over to Dale.
So I've been doing some solar system observing, and the scene was actually pretty good. I share my screen here. I got some good pictures of Jupiter. There was a double transit, and I got my best ever picture of Mars. So there is one of the best pictures I've ever gotten of Jupiter, and got 3 moons in it.
Yeah, we thought the mouse was one of those.
Mm-hmm.
These were all done in the last week. That's my best ever photo of Mars, and it's hopefully going to get
That's
better.
very nice.
Better this season here. There's a little bit of shadow still, so another month to go before opposition. And so this was the double transit. This is my mouse, Ganymede, Europa, and Io here is to the left. So I got it just as this larger Ganymede shadow just hit. But I made an animation. I don't do this very often because it's a lot of work. But
Oh,
I
wow.
thought this was a good use of it. 18 frames here over about an hour. And that's it.
Very nice. Everybody loves it. Many thanks from the audience, Dale.
All right.
All right. Yeah, I got in a bit of observing both up north in the dark skies of Alcona County and also actually in Dearborn. We broke out the old 10-inch, which has a not collimated finder scope, but that doesn't matter when you're looking at Jupiter and Mars's current opposition. So we had some good time with Jupiter. Saw the moon last week with a lovely terminator that was going through the Bay of Rainbows, aka Sinus Iridium, and a really kind of terrible view of Mars because the scene was lousy. But you could just make out part of Syrtis Major in the ice cap. So pretty cool. So we highly recommend that you all take a look at Mars. All right, anybody from the audience here in Cranbrook got some observing to report or some astrophotography? Bill, what you got?
The setting,
Yes.
6 o'clock, you're gonna see a setting on. The totality starts at 5:13, 5:12, something like that.
I read the maximum eclipse, it's almost 1 minute to 6.
But what I'm saying, you may not be able to see it as well if you'd like because of the word is on the horizon. What I'm saying, if you want to get the red, 5:30 would probably be the best time.
Anyway, get your cameras out, 5:30-ish, you'll have a great opportunity.
Yeah, and I have a brand new iPhone 13 mini with an actual good camera because I finally had to give up on my 4-inch phone with a terrible camera. One of these little babies, you can take a really good camera phone picture. We encourage all of you to at least try camera phone astrophotography because the results can be pretty surprisingly good these days.
Ross is not in the audience. I will say this instead. Don't use your camera, just look at the damn thing.
And Jeff McLeod does chime in with the words of wisdom of Gary Ross. Don't use your camera, just look at the thing. But a lunar eclipse is long, man. You can do both. You can do both.
Want to get a good picture?
Okay. We're breaking down in the brouhaha. All right. I have many good memories of lunar eclipses, including freezing my toes off here in Cranbrook in 2007. And then freezing my toes off again about 10 years later. Anyway, lunar eclipses are awesome. Okay. We have, if there's no more observing reports, then we got to get on with the show. Adrian, are you able to hook up Ken? Let's run this guy.
You're gonna do it.
Yep. Where's your tablet?
Right there.
There's your tablet. All right, so you're gonna lose the room temporarily. Those of you online, you just lost the room. Now, fire that up. So now you're gonna see. Do that. We're gonna pick that back up.
Get up here. Here
We're
we go.
gonna move the video camera to the board.
Okay, I guess we're ready to go. Do you have it?
Yep,
We're good.
I have it in there. So they're seeing this.
Yep.
We're seeing that. We're all getting ready to start.
Okay. Ready for me?
Yep.
Okay. Well, the first position is the president, and she can't run again. So, although we'd like her to, but she can't. So what we're going to have to do is we're going to have some nominations for president. And somebody suggested, this is the Warren Astronomical Society election 2023. This is the titles and qualifications. The office of principal officer of the corporation shall be the president, first and second vice president, secretary, treasurer, outreach director, publications director. However, the board may from time to time appoint such additional officers as is deemed appropriately. They must be at least 18 years of age, must have been a member in good standing for 1 year, must maintain his or her membership in good standing during the term of the office. The nomination committee consists of one of 3 members who are not seeking nomination, should be named by the board of directors at its meeting preceding the annual meeting. Oops, I didn't want to do that. I hate computers. Okay, there we go. Okay. All right, let's move on. For president, by the way, we already had a request for this, but the nominations are open. The president shall preside at all the meetings of the board of directors as chairperson of the board of the corporation, and shall have each other powers and duties as may be assigned. You don't have to, it's a suggestion, assigned to him by the board, provided they are not inconsistent with these bylaws. President shall be nominations for the position of president of the Warren Astronomical Society.
I think you have to officially ask him to.
You do have to officially.
Yeah, you do have to. Do you accept the nomination for president? Okay. Well, we always get that done, don't we? And so therefore, we'll close the nominations, and all in favor of Bob Tremblay as our new Warren Astronomical Society president, please indicate it by saying aye.
Aye.
Those opposed? Congratulations, Bob Tremblay. You are now the president as of January 1 of the Warren Astronomical Society. Okay, this next one is a little bit, but we'll do it anyway. Oh, by the way, there's your gavel. Okay, first vice president, program director. What's that? Well, again, let's just give the requirement. The first vice president and the first vice president, in absence of the or inability of the president to serve, shall perform all the duties of the president. First vice president is program chair, as program chair, shall solicit meeting presentations and guest speakers, planning and maintaining the presentation schedule, planning special presentations, communicate and coordinate with the meeting venues. In addition, the first vice president shall be a member of all committees that are appointed by the president, and the attendance of the first vice president at all committee meetings shall not be mandatory. That makes you happy, doesn't it? In case you decide. Okay, we have a suggestion. The board has put Jeff McLeod in as that, but we are opening these 2 nominations for vice president. What's that? We wanted him as second VP? Is that what it was? Oh, is that right? All right, well, I need a nominee for the first vice president then. What's that? I need a nomination for first vice president. Do we have one from anybody? Okay,
It's declined. Okay. Do we have any other nominations? Vice President?
Speakers, we will help you. It can be done from the comfort of your own home. A lot of it's done online these days.
You put in for a second.
What's that? That's what we put in originally on the advice of our president, but if I got it wrong, I got it wrong, so that's okay. Okay. We do not have a name at this point. We're going to pass that and go on to the next.
Close it, Ken. On two. Yeah, this is where Riyadh Maggie submitted Jeff's name to be second.
Yeah, 'cause he's termed out.
Yeah. Yeah.
Okay.
That's where the confusion is.
So we can now nominate Jeff at this point in time. Okay.
Second the nomination of Jeff McLeod as Riyadh's chosen successor.
All right. Any other nominations? Going to close the nominations for, we're going to close the nominations for second vice president. And all in favor of Jeff McLeod as second vice president indicate by saying aye. All opposed? Congratulations. Jeff, you are now second vice president. All right, let's move along.
I don't want chips.
Is Mark Marquez still?
Yes.
Yes, okay. For secretary, we have appointed Mark Kezier as a continuation of this particular position because he is eligible to do that. The secretary shall be custodian of all original records and documents of the corporation, keep the minutes of all meetings of the board of directors and of the executive committee, notify all members of meetings, perform all of the duties that are incident to the office of secretary or that may be assigned by the board or the chairperson and that are not inconsistent with these bylaws. Are there any nominations for the position of secretary? Got a second? All, any other nominations at this point? Mark, do you accept the position? Good. Okay. Then we close the nominations for secretary. All in favor of Mark Kezier as our continuing secretary? Opposed? Congratulations, Mark. You are now our secretary. And for treasurer, Adrian is still eligible for that? Is that correct? Good. Any opening the nominations for treasurer? Any nominations for treasurer? Good. Any seconds? Okay. All in favor indicate by saying aye. Oh, do you accept? He accepts it. That's one of the things you don't have to ask. You know, he accepted it. Okay. Any additional nominations? Move for entertain a motion to close the nominations for treasurer, which I should have done before. All in favor of Adrian Bradley as our treasurer indicate by saying aye. Opposed? Congratulations. You are now the treasurer for another term. And can Kevin continue? Yes, he can. Good. Okay. This is for outreach. This is to plan major public events, solicit volunteers for said events, communicate with the park systems, educational groups, and other astronomy clubs to satisfy the corporation's purposes cited in section 2.01A. Are there any nominations for outreach director? Any second? All in favor indicate by, oh, wait a minute. Is there any other nominations? We'll close nominations.
That being said, all in favor of Kevin McLaughlin as our outreach director, indicate by saying aye. All those opposed? Congratulations, Kevin. You're back at it. Isn't that a nice picture? And for publications, can Dale continue? He can, good. Any additional nominations for publications director? And don't you dare step forward.
Name of JLT or award-winning publications director for his third.
Dale, do you accept the nomination? He said yes. Okay. That's all right. I see him. I could see his yes like that. Okay. Any additional nominations? Then therefore, all in favor of Dale Teamy as our publications director, indicate by saying aye. All opposed? Congratulations. Dale, you are still our publications director, our award-winning publications director. Okay. There is no bylaw change. Okay, now we have an issue with the first vice president.
Yes.
Well, what's going to happen is, Bob, you'll probably get to appoint one temporarily. And at this point. What's that?
Vatican still needs it.
Has there ever been any indication from Riyadh from doing that? I was wondering.
I have some ideas. We have a month to sort it out.
We'll discuss it. Okay, what we'll do. That's what we'll do. All right. Then therefore I entertain a motion to close the nominations. Second. All in favor? Yeah, right. What's that? Yes. We're closing it. We're closing the election at this point in time.
Yeah, you close the elections, and then the next one will be an appointment.
Yeah, then we go consult the bylaws.
Right. Any additional comments about this? And I think we've gotten through it again, haven't we? I like that plan. I like that plan. Thank you very much for your time. And we're all set to go. Okay.
All right, pictures of the new board, which the same board, only.
It's not gonna go on the internet, is it?
We have the banquet, so it doesn't leak. All right, facility and switching back to the other computer.
Is off.
Okay. All right, we're bringing you all back in, and Tim, we're gonna figure out how to set up your live presentation. Yeah, but if he had a tablet, we could hook him into it. Yeah,
This is their device, so they can just leave it for them.
yeah.
All right.
Let's do this. Yep,
Okay. We have a break.
yep, we get it going. All right, let's go back to grid. Let's go back to, oop, wrong button. Integrate webcam. So now you're seeing me. All right, so we're back, and any more business before break?
All right, gang, since Mark Kedzier has thankfully worked out our snack issue, it is now snack time. Again, the snacks are not free. Please put $1 in the jar. Do we have a jar? Perfect. I can't see it from here. Yes, Adrian can do change. Those of you at home, please, smoke if you got them. Yeah, bring your own bottle, etc. In the interest of getting out of this room in an orderly manner, we are moving up the talk to 8:30. So Tim is going to go live at 8:30. We have 20 minutes for snack break. Have fun.
In a couple minutes, I think I'm going to log off here and we're going to log Tim in. We got about 5 minutes. Ask them if they can hear you.
Testing, testing, 1, 2, 3.
Those of you listening online,
We hear you.
let us know if you can hear us.
We hear you now.
Okay,
Okay.
perfect. Sorry for that.
All right.
You missed the boring part anyway.
Yeah, star formation. We'll
All right.
figure something out.
Let me get back to my.
Maybe we'll post your slides later.
Okay.
Or something.
Sure. Where's my keynote?
Can you see the shared screen?
Not yet.
Now you should.
It's just saying Tim Campbell is starting to share content. It stops there.
Okay.
It's there now. Do you see the simplified periodic table with a few of the elements?
No, it's still stuck on the starting to share screen.
Oh.
Okay. Not yet. Okay, I see where you said that. Unshare for a second. Let's see what
Oh, I have to go up over to here. That's why I don't see it.
So you
Where
were
is it?
connected.
I gotta find my mouse.
There's your mouse.
You are sharing, so you want me to stop
Go
sharing?
ahead and stop for now. Okay, so
And now come back over here and start again?
share
Screen two.
to share. Okay, how about now?
Do you see a big yellow screen background?
Not yet.
You know what? I wonder if we're struggling with the speed at which we can share because of our internet connection.
Let me check that. Hold on. Let's go here and see what I get. Just do a quick test and see if it's a problem.
Well, it got there. Right?
Yeah,
so let us know if you see.
It's crazy fast.
Okay. That's not it. So I wonder what else.
Make sure the upload isn't being blocked. I don't know why.
Yeah, we don't know why we're saying he picked the screen that's broadcast to the rest of us here in the room. And it says here you're sharing your screen. So you all still don't see it over on.
Yeah, and it says I'm uploading
don't.
at 300 and
Yeah.
well 200
Are
and
you
something
seeing
now.
the upload?
The test. It's very fast.
Yeah.
So I don't know why. I don't know why it's doing this to you.
Yeah. You guys still don't see anything yet?
Not yet.
Yeah.
This meeting is being streamed live to YouTube.
Yeah. That's.
I don't have to. I don't have to do anything, do I? Just go acknowledge that.
They should be seeing your screen.
Okay. Yeah. I don't know why you're not getting it.
Yeah,
So I'm using WebEx and I don't see anything either.
Yeah, we're all connected.
Is it just black or what?
Yeah, just a black screen.
Interesting.
I'm gonna say we'll continue with the presentation. If you can hear the presentation,
Yeah.
we're gonna continue and we're gonna see if at some point all of a sudden the screen appears because I wonder something else is happening. I saw him share it. He shared it correctly. So everything that's going on the screen where we can see it, you all ought to be able to see it. But for time's sake, if you can hear him, let's go with the radio version for now so we can just continue on. And let's see if eventually something shows up to you all at home.
Does the camera, do you see the camera video of me?
No.
I didn't hear what he said.
I didn't hear that either.
Oh, no, we're not seeing any camera shot either.
Oh, you don't see the video of me either?
No.
Yeah, if you wanted to, you could stop sharing and see if they can see you talking, but then they don't get to see the whole screen. They just get to see this one part.
Right. Well, I mean, if you put your laptop on that camera and projected the screen, would that work?
It would. I just have to reconnect. We can
All right. Do we want to take a pause or do you want to keep going?
go ahead and keep going.
All right.
Let's keep going. We'll it sounds like they can hear you though, so
Right. Okay.
so let's continue, and I'll try and put them on this thing.
All right, so I'll keep going. So essentially, as I was saying, everything that we were made out of, when we went back to you want to make the apple pie from scratch. Well, this is how you make the apple pie, right? So everything is made in the hearts of stars or in things derived from the stars, other than essentially hydrogen, helium, and a tiny bit of lithium that came out of Big Bang nuclear synthesis. I love this other quote from Carl Sagan: "The cosmos is within us. We're made of star stuff. We're a way for the cosmos to know itself." That's borderline spiritual, I suppose, if you want to call it that. All right, and so now time for the fun stuff. So let's talk about spectroscopy a little bit. One of the simpler ideas that we like to convey, this is actually a slide I stole that we use in the planetarium all the time, is to explain the different color differences that we have in stars. And the color differences come from an idea that we call black body radiation. Stars are nearly perfect black body sources. They're not absolutely perfect, but they're close. And the idea is that the hotter the star, the farther, so this is the hot end of the spectrum to the left, and the cool end of the spectrum is to the right. And so you can see with the red star, this is sort of the black body radiation curve, basically all the stuff that it's putting out. And this is the visible light spectrum, just showing here only for reference. And you can see that most of what the star is putting out is to the right of the visible wavelength, meaning this star is putting out a lot of infrared stuff. It's putting out very little in the UV. But since it's putting out obviously more red than blue and violet, you see a red star. So that's pretty easy. If we take the opposite example of the blue star, it's the opposite, right? So the peak of the black body radiation curve is over in the UV side. You see more blue and less red, and so you see a blue star. So now when you look at Albireo and you see the pretty sort of orange, yellow and blue thing, you can say, oh, there's examples of it right there. Here's yellow though, right in the middle. This would be like a G-class star, and that's what we have. Okay, so now it's time for the demo. And if you guys on WebEx probably still can't see, even though I'm trying to do this, because unfortunately, I actually have video of everything that everybody is going to see in the room here. You would be able to see online. Can you pass these out? Those are yours to keep, but don't touch the film that you look through. So these are, I want to say 500 millimeters per inch. So these are diffraction grating glasses, and there's 500 prisms. 500, I think it's per millimeter. 500 lines per millimeter. There's a whole bunch of prisms lined up edge to edge to edge to edge. And they're so fine that if you touch the film with your finger, the oils in your finger will fill the gaps in the prism, and they won't work like prisms anymore. So, so with that, I'm going to wait for everybody to get these, and you can fold them up, have fun with them.
Go ahead and stop sharing. I've got the camera towards you in the screen.
Okay.
And we'll let them see. So what you can do is go ahead and stop the share, but you can still show the demo on the screen, but they'll see the camera.
The camera view.
The camera view.
Okay, so do they see this now?
They should see that as long as they see your camera.
Okay.
So let's ask them. Can you all see Tim and the background of that light on the screen? Those of you in the WebEx.
Not yet. Tim Campbell's section is showing up. It's just showing his name. It's not showing an image.
It's not showing him.
Yeah, but
No.
what about are you sharing yours, Adrian?
Yeah, well, no, I'm not yet because I don't have the URL, so I can't get back in. Your Mac should be using that camera, which I think we got it set up for.
Okay, so you wanted me to do that.
Yeah, you
I
go ahead
understand.
and use.
So if I'm on the camera,
Yeah, it actually, you should see it because you've got
yeah,
your
it's there.
camera
Yep.
shown.
And they can see that. Yeah. And that's what they should be seeing.
Yeah, that's what, so you all are not, of course, we're not seeing any of them, but. All right, that's a weird Mac mystery.
All right. Everybody has the glasses. All right. So I'll go on with this. All right. So the first thing I want to talk about is just, this is an ordinary incandescent light. So if you would, please take your glasses off. I'm going to turn this on. May hurt your eyes. Sorry, I don't have a dimmer on it. Jesse had a little dimmer on his. This is an ordinary incandescent light that I picked up at the store. And if you look at this through the glasses now, you should see a big, brilliant rainbow coming off to both the left and right side. Is that what you all see? All right. And you're not really looking at specific elements here. This is just tungsten, and we're making it really hot. And so when I talked about black body, sources, black body is just heat, right? If I'm a blacksmith and I take a piece of iron and I put it in the forge and I heat it up really hot and it glows, that's black body radiation that you're seeing. And the more it cools off, the more that curve sort of slides over to the long wavelength side of the spectrum. Everything that is not at absolute zero is able to give off some heat. And that's what we mean by black body radiation. This is another kind of cool toy to demo. I'm going to turn this on. I'm going to leave all of the LEDs on. And when you look at this, you should now notice all the LEDs are sort of staircased off to the left and staircased off to the right. And the idea is, I think that the red is the farthest away, and the one down at the bottom, it's the closest in. So the longer the wavelength, the more it's able to bend it. And that's the principle by which these glasses are going to work. So I want to get used to the idea that by changing the wavelength, the glasses will notice this in a shift in where the object shows up for you in the glasses. So with that, I'll see if I can show this to the people in the audience. So here's the sort of build. There we go. And so this is me holding a giant piece of diffraction grating film in front of it. If this does actually get captured on the video, you'll be able to see it. And you can see how it's shifting it over. So that's what people on the internet would be seeing if it was working. Next up, I have the hydrogen tube. So again, glass is off, and I'll just turn this on. And there's something I'm going to want you to notice right now, and then something I want you to notice later. So you see this sort of purplish light here. And when you look at it through the glasses, you should see, if I can get this to fast forward. I kind of want to scrub it ahead. I wonder if I can control that. No, it won't let me control the scrub. So the idea is when the diffraction gradient glasses are on, you're going to see those 4 lines of the Balmer series. So very strong red, which is the hydrogen alpha line, that's 656 nanometers. And then you'll see the sort of I'm going to say it's like a light blue, green line, and then 2 dark blue lines that are really, really hard to see. Oh, you can do that. Nope, not that one. Oh, there it goes. All right. Can I make this scrub forward? No, I guess I can't make it scrub forward. Okay, so that's the hydrogen tube. I'm going to turn this off, and I'll move on to the this one. This one is helium. And you can see the helium here. Actually, Adrian, you do this.
So I'm just gonna move the camera like this.
Does it show up through there?
That shows up. They can see there. If you look at Kim Burton's laptop, you should be able to see something. Might be able to see something. Can't see it. Oh, there it goes.
Need to change the setting. He's got the background blurred or removed.
Nothing showing up through the camera.
Yeah, that should. I mean, you see it with your eye, right?
I see it with the eye.
Go off to the side, maybe?
It's that.
Can you flip the camera to the other side? Is it reversible?
I thought it was.
Hit your video button. Stop video mode. Select the video. Full camera. There you go. Now do you see it? See if just the light will show up itself.
Adrian, can you hear me?
I can hear you.
Yeah, I think he's got the remove background setting set up. So we can see your silhouette and the background gets removed. So
Yeah, I just flipped the camera.
yeah, we see his black screen now.
So
Oh,
now you're
there we
seeing
go.
me
Now,
and you're
now we're
seeing
seeing
the
something.
presentation. I want to do this. Okay. Now you guys are seeing stuff.
There we go.
Oh, are they?
Yep.
Okay. And actually, if you hold this just a few feet away and off to the side, you can see the colors.
You can see the colors.
You see that?
Yep, we can see it.
Yep, there's
All
the
right.
colors right there.
Found a way. All right, cool. All right, so on this one, you see a lot more colors and especially a intense sort of peach color in there that you're seeing. Okay, good. All right, now let's move on to the next one. And this one I'm going to make you guys guess. So the first one was hydrogen, the second one is helium. Like every presentation you see, they're all going to do hydrogen and helium.
Yeah.
Way mine. Okay,
All right,
there you go.
there you go. So without the glasses, you see the color? And you've all seen this color before. I know you have. So we got one vote for neon. Anybody else going to go for a vote? Anybody? Anybody? So it is indeed neon. So, and you can see with neon, there is a crazy, crazy, crazy number of lines in here, right? One of the patterns that you should be noticing is the more complicated the atom, the more complicated this sort of colorful barcode that you're getting out of it. Just sort of keep that relationship in mind. It's kind of simple. All right, and then I'll do one more. And this one I never give away. I make you guess it. All right. There you go, this one. Now, everyone has seen this color in nature. Any guesses? Come on, you got to play along. What was it? What was it? There probably is carbon in it, yeah. Yeah, there's nitrogen in it, yeah, sure. What's that? Air. It is in fact air. So every person who's ever lived has seen this because every time lightning strikes, you're basically turning air into a plasma, and that's effectively what you're doing inside this gas tube. So this is effectively lightning in a bottle, if you want to think of it that way, which is kind of cool. So I love doing that one. All right, so with that, I'll show you very quickly. So there's a reference spectrum up at the top. And there's a sort of a refresher of what you saw when you saw the hydrogen. And these lines over here, you probably struggled to see these. In fact, you might have struggled to see this one. This is easy and this is easy. That's a little more hard. And I really don't see those myself. But they are there. There's a couple more that are actually off in the UV side that don't show up at all. On the helium, this is what you saw. It's dominated by this sort of peach colored thing here, but you see all those things. And then lastly, the neon one that we showed, just a whole circus full of these things over here with all these brilliant colors, but all on the red side of the spectrum. Nothing is over on the blue side of the spectrum. Now I want to go back to this one, which is the hydrogen. I'll turn this back down again, if I can find the power switch. Okay, look at that again. And compare that hydrogen. Does it look precisely like this hydrogen here? The answer you are searching for is no. Do you notice a whole lot of ghost lines in here? Okay, you know what those ghost lines are? It's an impure sample. So it's an impure sample. This is not pure hydrogen. So it's an old tube, other stuff has leaked. It's now got a lot of air in it. If it were a brand new one, you wouldn't be seeing those ghost elements in there. And by the way, that should help to reinforce another idea that if there's only a trace amount of it, you see it as sort of a ghost spectra. And if there's a lot of it, if it's really dominating, you'll see the really bold stuff. And so we actually do use that when we study stars to figure out what they're made out of and how much. All right. So this is actually a very important slide on why this even works. So I'm basically creating a phony baloney atom here, and I've got my atomic nucleus in the middle. So in the case of hydrogen, this is just going to be my proton. And then these represent the energy states of the electron off here to the edges. And here's the idea behind how this works. When a photon is wandering by, and it basically happens to hit this atom, it could be any number of wavelengths for that photon. If it happens to be one of those magic wavelengths in the Balmer series, those 4 dominant bars that you saw that we threw up a second ago, if it happens to be one of those, the hydrogen atom will steal it and the electron will jump into a higher energy state as a result of that happening. And then moments later, it will drop back to its ground state or rest state. And when that happens, it will re-release a brand new photon in precisely the same wavelength as the wavelength that it absorbed. So in the case of this red one, it's 656.28 nanometers exactly. So if I had something that would say 660 nanometers or 650 nanometers, it would fly right through the hydrogen atom as though the hydrogen wasn't even there. And there's the next line and the next line and the next line. And so that's basically how you're getting the colors working out of this. If, by the way, you have a something that's emitting these wavelengths, you'll see a black background and the lines will be lit up, and we call that an emission spectrum. But usually when we're studying exoplanets, we kind of are doing the opposite of it, and we actually even do this with stars. You have a hot black body radiation source. So you actually see all the light glowing here, and then you'll see black bands missing. And so basically if you run black body radiation through, so all wavelengths, running it through, let's say I had the world's biggest gas container full of a whole lot of hydrogen gas, the hydrogen gas would subtract from the black body radiation, and you'd see these absorption lines, also called Fraunhofer lines, for the man who discovered them. And so that's actually very important to understand the emission and the absorption for reasons that we'll get into shortly. So let's get into stellar classifications just a little tiny bit. So there's a whole history of how we went through stellar classifications. I always thought it was crazy that it's, oh, be a fine girl or guy, kiss me. It's like, why those letters? Why isn't it just like A, B, C, D, E, F, G? There's a whole history that I won't go into behind how we ended up with this orbit. This particular order. They were actually ordered differently, but they were coming up with subclasses. And so when Annie Jump Cannon came out with the Harvard system, originally she was basically getting rid of the noise and said, these are the main ones though, and so it happens to be these. So this is the ones that you're stuck with. Not very many O-class stars, but those are the biggest ones. At least 16 solar masses to be an O-class and 30,000 degrees Kelvin surface temperature, excuse me. And so the Harvard system classifies these stars based primarily on the surface temperature of the star. If you actually look it up in star catalogs, you'll see 3 components. You'll see like, if I pick like our sun is a G2 star, but there's the numbers at the decimal digit that follows 0 through 9 indicates sort of the sub-level of heat. So for example, a G-class star, is there, is 5,200 to 6,000. And so if you're on the hot side, if you're 6,000, you'd be a G0. If you're on the cold side, at 5,200, you'd be a G9. And so if you're someplace in the middle, so we're G2. So we are toward the hot-ish side of the G-class. And you're someplace in there. There's also a Roman numeral component, which has to do with how bright the star is. So that's how they came up with this system. And here's the interesting thing. So now here's all the stellar classes that we just talked about on the last slide, but these are actual spectra that have been captured of representative samples in each one of these classes. And we've sort of annotated to say, here's where the helium lines should be, here's where the hydrogen lines should be. And you'll notice some weird stuff going on. So for example, down here in an A-class star, you very strongly see these helium lines here and here and here. But you don't see, it gets kind of weak. Notice that down here, these lines are getting weaker and weaker, and you don't really see them very well up here. I guess I see, no, here's the other hydrogen line. Very, very weak. This one isn't even visible at all. And so this is an O-class star. It should be loaded with an insane amount of hydrogen. So how do you have a star that's loaded with an insane amount of hydrogen and doesn't really register as much hydrogen? And so the funny answer is, this star is 30,000 degrees Kelvin for the surface temperature. Whoops, didn't mean to go there. 30,000 degrees surface temperature. And you can fuse hydrogen into helium at only 16,000 Kelvin. And so this star is so hot that it's basically ionizing most of the hydrogen, stripping the electrons off of the nucleus of the atom. And so essentially, remember that slide where I showed you for the absorption and emission, you have to have the electron changing states. Well, if you strip the electron off of the atom, there is no electron to be changing states. So the star isn't completely devoid of no intact hydrogen atoms. It's just not as many of them as an ordinary star. And so as a result of that, O-class stars actually don't register as having a lot of hydrogen on them as a result of it. And so we can sort of take these absorption strengths over here and characterize this. So I can say, well, when we're at like B and O-class stars, we tend to see stronger helium lines. And there's the helium there. And so we get a little bit of that there. But we don't really have much in the hydrogen. Here, we have stronger hydrogen lines. And so you can see them represented there. Down here, we get stronger calcium lines and so on. And so you can kind of like, based on what your spectra is when you're analyzing these stars, help figure out the classic spectra of each one of these stars. And now you know what you're looking at. And when you know what you're looking at, you kind of understand an awful lot about what relative size that star must obviously be and what temperature it must be. And so you learn a lot about that star by being able to classify it in this way. So redshift is another fun thing that we get to do. So here I have this silly image of an ambulance, and I have two observers watching this happen. When the ambulance emits a sound wave off of the whale, if it were not moving, if we're just parked, letting its siren blare, each wavelength would be spaced out nice and evenly from the wavelength behind it, and evenly in all directions. But because it is chasing the wavelengths that it just emitted, as these wavelengths are traveling forward, it's re-emitting one right behind it, but it's physically moved closer to you. And so you get this bunched up effect. And this results in a high frequency. And you get the opposite for the person behind it, where you get the lower frequency. And so this is the Doppler effect. And this actually does happen with stars and galaxies. And so we can get an idea of how fast is that galaxy moving away. But we can also do this with stars. So this is one of the ways to discover exoplanets, is if you have a star big enough to swing its host star. Because remember, in orbits, we don't really orbit the sun. We orbit the sun-Earth barycenter of the sun. It happens to be very close to the center, but Jupiter's barycenter is actually off to one side. So as it's coming toward us, the star is going away from us, the wavelength goes long, and now it's coming toward us and the wavelength goes high. And so astronomers can study this shift in wavelengths and say, okay, this star is being tugged around. Even though the planet doesn't actually transit the star, I can tell something is tugging it around. And I can get an idea of, based on how fast it's being tugged around, how much mass there must be, how far away it must be, and things like that. And you can estimate whether you actually have a planet or maybe you have a companion star that's, dead or something. And so that's that idea there. The other thing that we love to do is find these exoplanets. And so here's our stellar neighborhood. We've got a couple of satellites that have done this. Originally, it was the Hipparcos mission. It later became the TESS satellite, which is out there now, actually transiting exoplanet survey scope. And everything that we're circling here are all other stars that have one or more exoplanets orbiting them. I think we're over 5,000 now. By the way, this one, Hipparcos 89, whatever that is, it's also called Gliese 710. The significance of that star is it happens to be on a path with the sun where it will become very, very, very close to our sun in something like 1.4 million years. That's from memory, but it is expected to pass so close to our sun, is unlikely to pass inside the orbits of like the traditional planets as we think of them today, but is extremely likely to pass easily within the orbit of our Oort cloud. That's probably not good news for the solar system, only because you have all these stable Kuiper belt objects and Oort cloud objects and things like that. And it probably has its own Oort cloud. And so our sun will destabilize its Oort cloud. It will destabilize ours. And all these things that were previously in nice, happy orbits, minding their own business, get destabilized. And it could trigger another heavy bombardment period with things coming hurling into the inner solar system again. But anyway, the real point of the slide is to talk about the discovery of all the exoplanets and where those things lie, and the ability to use spectroscopy every time an exoplanet, because these are all discovered with the transit method, to be able to study the atmospheres of the exoplanets, if only you had a spectrograph that could do that. Another thing that you can do with spectroscopy is study redshifts. So this is quasar 3C273. So 3C just means third Cambridge catalog. That's just a name. It's like saying Messier catalog. 273 is just like the Messier catalog. It's the 273rd entry in the catalog. This is a stellar quasar. The name quasar, probably most of you know what a quasar is, but I'm betting a few of you have heard the word but don't know where it comes from. It stands for quasi-stellar. And the reason they called it quasi-stellar is after they had discovered spectroscopy, they wanted to stare at these stars and learn about the spectra of them. And so they found this star, and they pointed their instruments at it, and it did not have a spectra that looked anything like any star they had ever seen before. And they said, what the heck is that? Here's the periodic table. Here's all of our reference charts for what all the spectra should look like. Here's all of our stellar classifications for what those should look like. This thing doesn't look like anything. So what could it possibly, I mean, is it made out of stuff that isn't on the periodic table, except the periodic table doesn't have any holes in it? So it's, like, what could it be? And then finally, an astronomer noticed that it did have a matching spectra. It was just slid over a whole lot. And so here is, let's see if I can, okay, I've got a couple of builds in this. I might as well build it out. There we go. So I'll put in that and I'll put in that. So here is the reference spectra. And here's the spectra of where the normal lines should be. And here's the graph of the spectra of 3C273. That's what it actually comes in as. And you can see that everything is slid way over. So 656.28, which should be hydrogen alpha, is completely into the infrared. You can't even see that wavelength at all. This stuff that should be up in the high blue end is slid down into green. And the stuff that should be green is slid down into this like going yellow on them. And so when they calculate the redshift of this, they get a mean of 0.1582. That means that this object is moving away from us at 0.15, call it 0.16, the speed of light. So this thing is moving away from us at 16% of the speed of light. So that is crazy far away. I thought I had a thing that, translates to 2.44 billion light years away. And you can see this with your telescope. This is actually something amateur astronomers can look at. And then they scratched their head and said, you should not be able to see one individual star 2.44 billion light years away. And then they came up with the idea that this is probably an active galactic nucleus gobbling up everything in the area and emitting an insane amount of light as it does it. So let's get into the Webb just a little bit. So Webb has 4 main science instruments on it. You've all seen lots of images of NIRCam and MIRI, probably, but you've not seen anything from these. Well, you actually have seen some stuff from this. You maybe just didn't realize it. This is NIRCam, which is the near infrared camera. This is the mid-infrared camera. So you'd think it would be called MIRCam, except it came from a different supplier, and they called it MIRI instead of NIRCam. So this is mid-infrared, near-infrared. And this is near spec, which is the near infrared spectrograph. Now, the trick about this spectrograph that's interesting is it is able to take the spectra of lots of things in the imaging field all at the same time. So that's really handy when you have for example, a deep field image and lots and lots and lots of galaxies, and you're trying to figure out which galaxies are close and which galaxies are far away, and you don't have to sit there, you've seen these images, right? And they're like, oh, there's 10,000 galaxies in this photo. And you're like, okay, you don't want to be the person assigned to go through, okay, galaxy number 1, galaxy number 2. I mean, you're going to be there a while. So this is able to do the spectra of tons of things at the same time. And it really is a time saver for being able to figure out what are these most distant galaxies, because those are the ones they really want to study. So that helps you find out where are those most distant things that you want to study. This one down here is FGS's Fine Guidance System, and NIRISS is the Near Infrared Imaging Slitless Spectrograph. This is another spectrograph, but unlike this one that takes tons of spectras at the same time, this guy can only do one spectra at a time, except that one spectra is so sensitive that it can tell you what something is made out of down to the parts per million level of sensitivity. So it's really, really good. We have never had an instrument that could do this before. So there's a reason that this all becomes interesting. I'll go on to the next slide briefly, and then I'll talk a little bit about why the other one is interesting. This is that first image that you all saw. What was it? June 16th was the reveal, I think. And anyway, I'm a solar system ambassador, and I volunteered to be on this web first images thing. And so I'm attending all these meetings and getting all the prep work. And I'm talking to our contacts that are giving us the trainings. And I said, so when are we going to get the list? Oh, you can't see the photos. No, I don't want to see the photos. I just want to know what the object will be so I can go look up and do some data and have like a presentation ready to go so I know what the object is that I'm going to be talking about. They said, absolutely. There's like 5 people in the world that know what these targets are. No one is allowed to know. Even the other people at the Space Telescope Science Institute don't even know. You will find out at 10:30 in the morning, just like everyone else. And then the night before, there's Joe Biden on TV with this image. And I'm like, well, I guess I'm not on the A list. So here it is, image number 1. And this is the Webb's deep field image. It was taken in 12 hours. It used 6 of the filters. So there were 2 filters that were used for red component, 2 filters were used for green component, and 2 filters were used for blue component. Each filter was run for only 2 hours. And so when you add 6 times 2, you get 12. So this is 12 hours worth of data collection, only 12 hours worth of data collection. Now remember when Hubble did this, it was 10 days. And this did it in 12 hours. And to be fair, it really kind of did it in less time because it was only a couple hours per filter. The name SMACS 0723 is not the real name. Down here in the corner, probably it's hiding behind the podium. It's SMACS J0723.3 minus 7327. I know that really rolls off the tongue. But what is kind of interesting about the name is that actually maps to where it is in the sky. Right ascension component is 7 hours, 23 minutes. See, that's how they get the 723 and 13 seconds. And the declination is minus 73 degrees, 27.4 arc minutes. And that's how we got to that component over there. Now the Z value of this is 0.39, so it's 4.6 billion light years away for this massive gravitational source that they get to. And again, they can measure that with the, what do I call it? Not near cam, not NIRISS. Oh, for crying out loud, I can't remember the name. And I just said it. Anyway, it's the spectrograph that can take the spectrum of everything in here essentially simultaneously. Every time you see a diffraction spike, that is a star, photobombing in the foreground galaxy. The things in the background galaxy are outside our galaxy. So let's zoom in here. And this is the cool thing that they found on this. And I'll circle it over there. And there you go. That dot right there is the thing that showed up on this image analysis as being the most distant thing in it. It is Z value of 0.95. So 95% of the speed of light is how fast it is moving away from us. And it is 13.1 billion light years away. Now, when you think about that, if it's 13.1 billion light years away when the light started its journey, and it's moving away at 95% of the speed of light. So it's long gone by now. It's out, in reality, it's the true location of that is beyond the visible horizon. You would not be able to see where it actually is anymore. So that's the redshift stuff that we're doing. But I wanted to talk about what we're doing with NERIS on the web. And this is not the image. This is a diagram to explain how it works. So I've got a distant star, and I've got an exoplanet that's going to transit. What I want to do is take the spectra of this star when the planet is not in the way. And then I want to take the spectra again when the planet is in the way. And then I want to compare the two spectra. And the nice thing is remember we mentioned TESS earlier? TESS has already cataloged thousands of exoplanets. It knows where they are. It knows exactly when they are going to do their next transit. And so they just pick some nice juicy candidates, things that look like they might be in a habitable zone distance away from the star. Pick on those and say, well, when will one of those transits happen? And so rather than wasting valuable telescope time hoping to get lucky, they use TESS data to tell them precisely when to look at the star, and they get to watch the transit happen. And when that happens, they can compare the non-transiting versus transiting, and they can tell you what elements are present in the atmosphere of that planet. And this is the first time in human history that we've been able to do that. And so here is WASP 96b, exoplanet, and you can see they've identified clear traces of water in the spectra of this planet. Now, this is not the spectra of the planet directly. This is the difference between the spectra of the star and the spectra of the planet that they're able to do this with. They did it again. They also detected, I think, CO2. Now, is there life here? No, because it's a crazy, crazy hot planet. It's really orbiting fast. But this is really to just demonstrate that, hey, we can detect these things now. They do want to be able to figure out what are these planets made out of, how normal are we, what are most other things made out of. You might detect elements that really get you scratching your head. So for example, there are elements, oxygen should not be dominant in the atmosphere of Earth. There's a ton of oxygen on Mars, it's just not in the atmosphere. Oxygen likes to oxidize things, and when it does, it doesn't let go. But we have this little thing called photosynthesis going on that breaks those molecules apart and throws off the oxygen as a waste molecule. And until we had photosynthesis happening, we didn't really have much oxygen in our atmosphere. And so this is sort of an indicator to say, if you could find abundances of things in an atmosphere for which the only way we could think of those to happen would be biological processes, not abiotic processes, have you found a marker for life? Well, you might be being tricked. You might not have found a marker for life. You might just not have thought of all the various ways for that to end up in an atmosphere. But that either means there's new discoveries on how things can end up in an atmosphere, or maybe you did find a marker for life. Who knows? Either way, that planet has suddenly become extremely interesting. The one thing I wanted to do, how are we doing for time? Okay. So I'm going to show you one little quick demo real fast. Where's my, is it there? Got to get this to come back up. So I did just I promised you that I'd tell you how you can do spectroscopy on your own. And so I just wanted to show you the software. So this is actually a Windows virtual machine running on my Mac. If I can get this to slide in, I'm going to light up this RSpec software. This is the software. And I'll talk about the equipment. So what you need to do this is one of these gadgets here. This is a diffraction grating. You'll notice it's the size of an 1¼ inch filter, like the sort that would thread right onto the bottom of your eyepiece barrel, 1¼ inch eyepiece barrel. And this is called the Star Analyzer 100, so it's 100 lines per millimeter, is my understanding. But it's a diffraction grating, just like the stuff that you're looking through with those glasses, except this is a nice one. It's actually glass, it's not a film. And then I take this is actually my guide camera. So this is some ASI camera here, but I prefer to use this camera rather than a color camera. This is a monochrome camera. Color cameras are, and I'm just going to screw this on. Color cameras are, they've got their own internal filters in them. So they're filtering out things that human eyes don't normally see. They're biasing the spectra toward the green. And as light is going through there, each one of those little microfilters in the color filter array is altering the true spectra. And so you're not really getting true, yeah, you can use it as a learning tool, but if you wanted to do real science, you want a sensor that isn't going to be editing your spectra on the way to collecting data. So I just thread this on to here. I'll slide it in the back of a telescope. Smaller is kind of better. I found that if I used, say, a telescope with about a 500 millimeter focal length, like an 80 millimeter refractor, it works great. When I use the great big Celestron C14 F11 with a 3900 millimeter focal length, the giant monster that we have at the observatory, it doesn't work so well. The spacing becomes a problem. So that's why I kind of prefer doing it with a smaller thing. When you do that, I lit up the software here. Did I light it up? No, I didn't. And light this up. And so the website that you go to is rspec-astro. The guy's name is Tom Field, who developed the software. And this is what you get. This is the user interface. I would normally come down here and say, do I want to use a live camera or a video file or an image file? So I could have pre-captured video through my telescope, or I could have captured an image, or I could just tell it I want the live camera. Show me what's going on now. Well, I obviously don't have a telescope here in the room, and even if I did, we would see the ceiling. So I'll go ahead and pick image file. Here's a spectra of Vega. Now, up here, this is a little messed up. I have to rotate this image. I can remember how to do that. The rotate button there, and I'm grab this and I'm gonna slide it up and down, and I'm trying to, there it goes. Oh, I gotta go to the top. Won't let me rotate far enough. Okay, I got it, there we go, so it's there. And then I slide these little lines up and down. And here's the idea. Let's suppose I have more than one, this only has one star. By the way, this is an actual image of the spectra of Vega. So this is what you would actually get. And so over here, that's actually the star. And this is the smear of light that you get through the diffraction grating of the star. And you could have a lot of stars in there, but I can adjust these two lines to sort of bracket out the stars that I want the computer to ignore. And the only thing that it will pay attention to is the stuff that showed up between the two lines. So that's simple enough to understand. And now that I have that, I go over here and there's the huge spike in intensity from the star itself. And then here is the spectra. And so what I need to do is turn this into, this is an uncalibrated image. So it tells me I just have pixels down there. So I need to calibrate this. And to calibrate it, I think I just click the calibrate button. And it says, pick on pixel number 1. And it says, what is the wavelength? And since the wavelength is 0, it's the object itself. All I have to do is go up here and pick it. And so that's pixel number 73. And then it lights up on that. Pick on pixel number 2. And they suggest you pick on hydrogen beta, but you don't have to. But it's easy to spot hydrogen beta. It's usually a big dip in the light here. So it shows up well. So I'll pick on that. And then I apply and watch pixels is about to change. So now I'm going to hit the apply button. And boom, all of a sudden, now it is measuring angstroms. So now it truly knows how far away things are. I can bring up reference stuff if I want. So if I wanted to bring up, let's see, there's a reference slide. Oh, I know what I want. It's up here. So I can pick on this. I could say, show me the hydrogen Balmer lines. And it lights up where the hydrogen Balmer lines should be. So there's the hydrogen alpha line there. So you see a little tiny dip, just a little one. And there's a hydrogen beta line there, and you see a dip. And then there's hydrogen alpha, beta, gamma, and delta there. And so you can kind of see those little absorption lines that pick off. But the other thing I can do is I can pull up, I actually don't know the stellar class of Vega off the top of my head. But if I did, I could open the reference library, go into the reference library, and I could pick something. So I'll just pick a G2 star. That'd be like our sun. I'll move that out of the way. And what it's doing is it's overlaying the reference spectra with the spectra of my star. And I can say, well, does it match? And I go, not so well. And I could fish around in here until I could find things that actually do match well and help me classify what this star is. Now, there are all sorts of really interesting experiments that people have done with this. That thing with Quasar 3C273, that was actually an example done with this software. The redshift, that was measured by an amateur astronomer using the diffraction grating in this software to measure the redshift of a galaxy. There's another really cool experiment where they captured a type 2 it might have been a type 1a supernova. Anyway, it was a supernova, and they wanted to know how fast was that cloud of ejecta being shot out from it, mapped to something like 22 million miles an hour. But what happened was they were measuring the redshift of the light from the supernova relative to the light of the galaxy itself. And they were able to measure that and say, wow, so the gases in this thing are basically blasting away from it at that particular speed. And they walked through how you do the math. So it's kind of an interesting thing that you can do with the spectroscopy, whereas normally we stare at the stuff and we go, oh, it's really pretty, or we can take our cameras and take beautiful astrophotos. But this is if you really wanted to get into science and started classifying things and you wanted to do it as an amateur, you could actually do it with this stuff. This diffraction grating, I want to say I paid $200 for it, and the other equipment I already owned. And I don't remember what I paid for the software. It wasn't too much money for this. It's not free software. You do have to buy it, but it wasn't too bad. So it's actually kind of fun to be able to do that, and I wanted to be able to show that to you. So with that, the only get out of here and get back to my other presentation here. Where's my mouse? There we go. Click this. We call spectroscopy the gift that just keeps on giving. So with this, we can detect, and I already mentioned, temperature, composition of the object, the size of the object. Remember the stellar classification tells you what the solar masses are. The mass, especially if it's doubles, so you have an idea of what the mass would be based on stellar classification. But if it's a double star, you can actually use the redshift of the spectra and tell exactly what the mass is. Relative motion and velocity, because you're getting the redshift that you can measure out of it. The presence of exoplanets and what is in the atmospheres of those exoplanets, as we discussed before. The gas pressure. Now, I didn't talk about gas pressure. Oops. I did not talk about the gas pressure. The gas pressure is based on the pinching in or stretching out of the spectra. And I think, is there one more? Oh, and the magnetism. So all of that can be done just through studying the information hidden in the light. That's all I have. And I apologize that we had some the glitches and it wasn't really easy for some people to see. But if there's any questions, I can take questions. Yeah. Yeah. Oh yeah, yep. You're talking about, yeah, in Lake Angeles? Yes. And through that, by the way, so I showed helium, right? Helium was kind of a weird thing because they noticed that showing up in the sun, and it was an element that did not exist on Earth, so they thought. And since it only existed in the sun and did not exist on Earth, they named it Helios, Helios after the god of the sun. Yeah, and then they discovered that when we started mining for oil that they found pockets of it in the earth, and then we wasted it on party balloons and we don't have a lot anymore. Oh, is it?
Getting into it. Accessing it. Accessing it? Yeah.
Is it possible to visit? Oh.
Property owner has locked it up. Website. So,
Other questions? Yeah.
Show this chart where the very hottest star.
Yeah. Oops, if I get this out of the, I got to go forward to this one. That's what you want.
Yeah, that one. Is that saying that the helium now is less at that point in time? Is that what that's telling us, or what is it?
What it's saying is that you're seeing more helium absorption lines,
Okay.
and these are absorption lines, not emission lines.
Talking about, obviously when a star burns its hydrogen and helium, the little nuclear ends, and then you get the star. And you say these stars die pretty quick. So
They go through them, but I refer to it like transmissions on your car and how many gears you have. Bigger mass stars have more gears, which is to say they're going to burn through their hydrogen and produce helium. Now, the problem is when you're burning hydrogen initially, you're at 16,000 Kelvin in the core. And it's trying to blow the star apart, and gravity is trying to squeeze the star together. And so you've got this stalemate going on, and it's stable for a little while. But the stalemate doesn't last forever because you will eventually run out of hydrogen, but you will not run out of gravity. And so gravity will ultimately win in the end. So,
does that have anything to do with that?
well, this may be because it's able to, I don't know if this is its main sequence where it's just turning hydrogen into helium. In our star, the helium is locked up in the core and it can't really convect out to the surface. It may be that for this star, it's able to get out to the surface, is my guess. And the reason I say that is because remember, this is 30,000 degrees Kelvin and it fuses at 16,000 Kelvin. And so my guess is, and to get helium to fuse into oxygen requires 100,000 Kelvin. And you don't have that at the surface. So that would kind of explain why the helium lines would be showing up on the surface, I think. But I'm not an astrophysicist.
So that question from online.
Yeah.
What effect does atmospheric dispersion have on earthbound spectral analysis?
Oh, that's a good.
Because the orientation, of course, they just lost.
Yeah. So
You got the question.
That's a good question. So the question is what effect does atmospheric dispersion have? So I will tell you, it does have a big effect. I was at the observatory. One of the things I wanted to do, and I ultimately was not successful, is remember you saw that I could load a video file? So I wanted to shoot video, and I don't remember which star I picked, but I picked something relatively high in the sky. And the seeing conditions were terrible that night. And one of the things you can do in the software, I won't go back to the software to show it, is instead of showing the analysis of just a single frame, you can get it to average, like show me an average of the last 10 frames running, put everything together. And you could literally watch the spectra like sort of resolve and get sharp, and then all of a sudden get so distorted that you couldn't even see the hydrogen beta absorption line at all. And so that was quite a challenge. And so I was like, you kind of do need, you can do it in light polluted skies, but you kind of need somewhat stable skies. And so if you're getting low in the sky and you're having more atmospheric dispersion, or if you're having quality issues with the seeing conditions, it's going to mess with the quality of your spectra. When things are low in the sky, you're looking through like 6 times more air mass than when you're looking up toward the zenith. And so you've got more interference of maybe our atmosphere absorbing things out of the spectra as well. Yeah, other questions? Oh, wait a minute. Yeah. You can totally do this. Now, major contributions, there is a group, there's a groups.io group for RSpec Astro where people discuss all the things that they're doing. There are some pretty cool things that I've seen out of it in terms of a major contribution, like, does anything show up and get published in a physics journal? I don't know if I've ever heard of that from an amateur grade stuff. The resolution of what this diffraction grating will do is far lower than what a professional diffraction grating would do. I'm getting a whole lot of angstroms all jammed on just one pixel, so I can't tell them apart. But on a professional grade piece of equipment, I'm really separating out the angstroms to pixels much more finely to where I can figure out precisely what that thing is. Mine is kind of averaging things together. You can still do some pretty cool stuff with it, and any amateur can make this work. Yeah.
Software have a tool where it will convert speed that let's see is moving, shift and say the spectral lines. Or give.
It might. I'm kind of new to the tool, and he keeps adding more and more and more new stuff to it. You know, so one of the things when they talked about the Z shift, right? And so for me, so when I showed that quasar 3C273, and it said, oh, it's 0.158 is the Z value. And so what I did is I took the 656.28 nanometers and I divided that by the actual measured wavelength of the hydrogen alpha line, and I got like 0.13 something. And I went, wait a minute. It occurs to me that if you divide it out and it's 0, you know, now you're at the speed of light if your Z value goes to 1. And so I'm thinking, well, my Z value is 0.13, so shouldn't it be receding away at 13% of the speed of light? But the professionals say it's closer to 16% of the speed of light, which either tells me that maybe the data contributed by the amateur was wrong, or I just don't understand the process for how they compute the Z value. Either or both are acceptable answers. But you can have a lot of fun with it. Other questions? All right, thank you for your time and attention. I'll make sure that you get a copy of the deck. And so you can at least post that.